1858, Friedrich Kekulé presented science with the first workable model of the carbon atom. This is the classic representation of the simplest organic molecule, methane. Though revolutionary for its time, it has long since been superseded by today's more sophisticated model, patterned on the quantum theory of the atom. Quantum theory is based on wave mechanics, and this model is one of many modern visual renditions of methane bonding. In the planetary view of the electron shell, it was convenient to imagine electrons circling the nucleus in distinct pathways. Alas, nature doesn't work that way. Rather, experimentation reveals that there is a 90 to 95% probability of locating an electron anywhere within a region of space surrounding the nucleus. This cloud-like region is called an orbital. In this orbital model, the first energy level for any atom is called the 1s orbital, and it contains a maximum of 2 electrons. The filled 1s orbital for helium, or any other atom, is spherical and non-directional. In the planetary view of neon, the second energy level contains a maximum of 8 electrons. Since these electrons don't really move in perfect circles either, we'll transform them into orbitals. As we have just seen with helium, neon's 1s orbital takes on a single spherical shape as well. But the second shell is going to prove a little more complicated, as it is subdivided into 2 related types of orbitals. A 2s spherical orbital containing 2 electrons, and 3 distinct 2p orbitals, each occupied by 2 electrons. Unlike the 2s orbital, however, the 2p orbitals each contain 2 lobes, which somewhat resemble dumbbells. So far, so good. But since we have separated the orbitals for the sake of clarity, we can now regroup them around the nucleus. Notice the definite orientation of the 2p orbitals. In order to minimize the repulsion between electrons, the orbitals are aligned along 3 axes at right angles to each other. Now, we'll bring back the 1s and the 2s orbitals, which we temporarily orphaned, and surround the nucleus with all orbitals. Note that the electrons in the 2p orbitals would be, on the average, farther from the nucleus than the electrons in the 2s orbital. Because the energy of electrons increases as their distance from the nucleus, the 2p electrons are in a slightly higher energy state than the 2s electrons. Now, if you didn't quite see this energy difference, you're in good company, since this orbital model tends to become cluttered. Nothing sacred about models, so we'll dismantle the component parts once again. On a simplified scale, the relative energy levels of the electrons show up this way. And it's this view of the distinct energy levels of the 2s and 2p electrons that will help us understand the behavior of carbon. But first, we will call up the planetary model of carbon with its separate shells and begin to transform them into orbitals. Because the 2 electrons in carbon's 1s orbital don't play a role in molecular bonding, we can mercifully dismiss this orbital. But carbon does possess a 2s orbital with 2 electrons and 3 2p orbitals containing the remaining 2 electrons. No, you're not going mad. You heard correctly. 3 orbitals containing 2 electrons, which raises the interesting question, what occupies the third orbital. Quantum theory is as quirky as a slot machine. Only two of these 2p orbitals can be occupied by an electron at any moment. But which orbitals, we can't say. Now, we will temporarily assemble carbon's 2p orbitals and its 2s orbital. In carbon's ground state, these related orbitals are at two distinct probability distances from the nucleus, which puts the 2p electrons, on the average, at a slightly higher energy level than the 2s electrons. Yet, when carbon bonds with hydrogen to form methane, empirical evidence insists that all four bonds are of equal energy. The solution to the paradox? Save appearances, save the model, and blend or hybridize the orbitals with a jolt of energy. Four entirely reformed orbitals of equal energy, all equidistant from the nucleus. We can theorize how hybridization occurs by returning to carbon's ground state, dismembering the model, and mounting the bonding orbitals on the energy scale. With a boost of energy, one of the electrons in the 2s orbital is kicked into an empty 2p orbital. Simultaneously, while the remaining 2s electron is booted up to an intermediate energy level, the electrons in the 2p orbitals drop down to its equivalent energy level. Now, we'll reassemble these hybridized orbitals to a three-dimensional model. These bowling pin orbitals are now given the shorthand designation sp3, where the S and the P indicate their hybrid nature. And for you sports fans who love instant replay, we can imagine the lightning speed hybridization taking place this way. A 2s electron jumps into a vacant 2p orbital, and instantaneously, all four orbitals transform into shapes of equivalent energy. Again, all four hybridized orbitals have the same size and shape and are pointed towards the vertices of a tetrahedron. At 109.5 degrees, the electrons have optimized their mutual repulsion. Now to continue. Since each sp3 orbital contains only one electron, it can accommodate one more electron in a covalent bonding arrangement. And hydrogen, with an eager electron in its 1s orbital, is a good candidate with which to share electrons. Hydrogen orbitals can hardly resist overlapping with carbon's orbitals to form methane, a stable molecule with four covalent bonds. In the next program, we'll watch carbon, the Lamborghini of the chemical world, put on a spectacular performance.